mass or solidity of smart contracts. But we wanted it to be expressive. By expressive, I mean easy to construct real-life business logic for the smart contracts, so that you don't have to write a lot of boilerplate code and complex constructions which are incomprehensible. So you need all the real, like, production-ready primitives. But it also had to be easy to be debugged, and we needed a test framework which allows you to write secure code with a lot of testing. And finally, it had to be constructed in such a way which would allow us to optimize the code very efficiently. And I'll talk about this also. So essentially, Zinc is a subset of Rust. It's a simplified Rust. So if you love Rust, you will also love Zinc. If you hate Rust, don't worry, we excluded the parts which you hate. And it was in part inspired by Facebook Libra's move language, because Rust is one of the most secure languages. Like it's a preferred language for cryptography these days, and if you want to write robust code, you write it in Rust more than in other languages, and it has reason why it's the case. If you write code in Zinc, you will be able to construct zero-knowledge proofs and create proofs in anything which Bellman can create proofs in. And by the way, you can also use any gadgets which are available already for Bellman in your code, and we'll cover this as well. But for now, the proof systems which Bellman supports are Groth 16 and Groth 17. Plonk, Marlin, Redshift, our transparent proof system, are coming, and they're going to be very efficient, like with all the efficiency of Bellman. But you will also have a second option. It will be possible to write programs which natively run on ZK Sync, our ZK Rollup platform from Meta Labs. So we will support native smart contract features that you won't even need to think about zero-knowledge part if you want to write scalable smart contracts and also private smart contracts. So it will be encapsulated there. So let's go through a quick tour of Zinc language. And just like, it's not going to be a complete tour, but just an overview of what you will expect. So we start with a simple program, which is a proof of pre-image of SHA-256 hash. Any program has the main function, which takes some arguments, which is your witness, and outputs some result, which is your public input of the circuit, or public output, whatever you call it. So here we take the pre-image, we deconstruct it in bits, then we pad the bits because the pre-image type is filled, and in our case with Groth 16 we work with elliptic curve, which only can represent up to 254 bits in the field, so we need to pad it to 256 bits and then put as input to our standard SHA-256 function, and you just get a result as an array of booleans. And by the way, all the highlights are coming from our Visual Studio Code extension, which you can just install in one click and have a nice experience of development. Now, I'm sorry. Zinc comes with Zargo, a package manager which resembles Cargo from Rust. So you can just create a new circuit. You have standard operations for all zero-knowledge circuits like setup, proof, and verify. But you also have a separate run command which allows you to simply run your program and see the results without creating proofs, which is going to be much faster. So if you just want to iterate on your development cycle, you will just work with this. And of course, Zinc is just Rust code, so you can also use it in part of your program as a library. This is how the input-output formats look like, essentially. So this is witness, the output would be the same, it's just a plain JSON. And what's interesting, you can represent complex data structures in Zinc, like you have in enum, you have some struct, you have some arrays, some tuples here, and your witness will just completely resemble the structure. So it's super easy to work with it. But we'll come back to this. Okay, we have variables. Oops, sorry. Zinc adheres to strict typing. So we have a Typesafe language with every type only assignable to another variable of the same type. And it's easy to define them. We have some simple type inference. We support booleans, integers, field elements. By the way, both signed and unsigned integers natively, which is not the case for many zero-knowledge proof frameworks. We have some complex types, such as tuples, arrays, enums, structs. We have immutability by default for everything. So if you want something to be mutable, you have to explicitly state this, just like Rust or functional languages, which is very, very important to writing safe code. Now, we have basic arithmetic operations, like whatever you expect from a language. So you have addition, multiplication, like all arithmetics here. You have comparison, you have Boolean operations. Types are correctly inferred, and you can only do operations in correct types. We have conditional statements, and you can have complex logic here. So you can use them functional style, but you can also use them in non-functional style. So we also have match expressions. We have a lot of syntactic sugar. So we have type redefinitions in language and so on. Like we just follow the Rust syntax there, which makes code a lot more readable. We have loops. They're special. We'll come back to this. And we have standard library, which covers a lot. So as I said, whatever is possible in Bellman, all the gadgets can be imported as a part of standard library. So we now have cryptography, we have hashes, we have manipulations of bit arrays, we have working with arrays, including parting, slicing, sorting, and so on. You can work with the fields, you have math and so on, and you access it the same way you would do in Rust. We have modules in Zargo, so you already can have multiple files, you can split your program across. Like the code base can be quite complex, and you can import them, and so on. You can define functions. We have some nice tooling for testing and debugging. So testing framework is coming, but debugging is already available with debug traces, which you, for example, don't have in Solidity yet. So yeah, let's compare to Rust, Solidity, and general purpose programming languages. What are the differences? First of all, Zinc is non-Turing complete. So we don't have recursion, and we cannot have unbounded loops. So you always have to specify the exact number of iterations in your loop, because it's zero-knowledge proofs, and we cannot yet do it efficiently. Like it will be possible in some time in the future, but it will require some advances in the proving technology. So for now, we just came up with this construction, which is slightly different from Rust. So you always have to specify a bounded cycle for your loop, bounded range. But you can also add a condition instead of writing like for, if, with some nested constructs. So you can, for example, here you could add some condition that sets the stop condition up, and then it will stop at some point. But while it will stop, it will still cost you 1 million iterations. So whatever the cost of this part here, it will be replicated 1 million times, no matter whether you stop it or not. Well, I'll answer at the end. All right. This cost structure is a little different. So it's just different. It's not more expensive than like anything. So some operations are more expensive, some operations are less expensive. For example, if you have conditionals, you will normally have the cost of this function plus the cost of this function overall in conditional. So again, this affects all zero-knowledge proofs just for the matter, because of the way zero-knowledge proofs are constructed. So this is important to take into account. Bounded loops, different cost structure here. So we will have a profiler which helps you understand what your cost currently is. You can play around with code and quickly see what are the changes so people can learn quickly. What we don't yet support from Rust, which we want to support, is templates. or at least some special cases like option and result. For now, we would have to use booleans, but we intend to support them because it's really handy. And same for templates. Sometimes it's really handy to not have to write a lot of boilerplate code. What we probably never support, or at least not for observable time, is some complex generics with type inference because they mess up the code. Like they give people ability to write very complex code which nobody can understand. And we don't want that for smart contracts. So we follow the move approach in this and say we want things to be as simple as possible. Move or Go, whatever you prefer, like things have to be readable. You look at the code, you immediately understand what it does. Like no magic, no you know, something under the hood which nobody sees. For the same reason, we're not going to support functions as first-class citizens, although it's a functional language, but it's just going to be too complex. And we don't have non-determinism, at least for now, which means you cannot write code which is not part of the zero-knowledge circuit, but which produces some values which you can use in the circuit. So those of you who are familiar with zero-knowledge proofs understand this, but we can talk more in depth later. But for now, no. Okay. So finally, the highlights of Zinc, like what makes it unique among other zero-knowledge proof construction systems. First of all the operations are safe. So you have like the math here is constrained automatically. You cannot have overflow underflow, which would be very expensive if you would do it yourself every time. But Zinc will infer whether you need it or not and to what extent. So if you just add a constant, it will be one check. It will, if you're adding two variables of different types, it will be different check. Like Zinc is an ability to better understand how to optimally create it for you. But you can feel safe as a developer. You're not going to make a mistake there. Same with like all operators are safe by default. You cannot have ambiguity, which you have in C++, or there's this bug from Tornado Cache, which they luckily found before anybody could exploit. But you see that the operator here is very similar to operator here, and they both work, but they do like entirely different things. So things like this are not possible in Zinc because it's like design decision to start with Rust and to pay careful attention to things like this. They should not be possible. So we have complete determinism, which means you cannot forget to make a constraint like we have here on the left side. Whatever you see here, what you see is what you get. If you can read this code, understand what it does, this is exactly what the code is going to be doing. And like not some hidden things which are really, really difficult to reason about. And we have assignments and complex conditionals, which is very, like this is super important. This is probably the main reason why we created Zinc. I only have 1 minute, but yeah. It's really difficult to make conditionals in zero-knowledge proofs because you would have to, like, to implement this in any other framework, you would have to go, and every time you modify this mutable variable inside a conditional, you will have to make a complex statement which has a select, which includes the previous value of this variable, and the combination of all the conditionals for the case where we are now. So if the conditionals are like complex and nested, it would be really, really hard for you to do this. You would have to think about it, you would have to go and modify it everywhere in the code if you make a change. Like, it's hard. Here it's super easy. You just see, okay, if, then this, then else, and this. And we optimize things for you in the background. And it gets even more complex if you have structs, because then if you have a conditional assignment, like if you have a struct assignment in the conditional, then you would have to do it for every variable in the struct, everywhere down the code, like on all the branches. It's really, really hard. So we do it for you automatically, and we will check that you only make these conditional assignments for the pieces which you need, not for all of them. And finally, we do a lot more optimizations. Like, this is a simple example. If we just had 2 expensive operations and conditionals here, we would have to, like, the cost of this would be 2 hashes. And hash is like SHA-256 hash is 25,000 constraints, whereas a conditional is just a few constraints. But we can optimize it nicely here by just computing the hash once from some witness which is passed non-deterministically for by the prover, and then in the circuit we just assert that the input is correct depending on the conditional. So this only costs you one hash plus a few more constraints. And there are a lot more things like with this which you can do if you have information about the types and about the execution graph of the program and so on. So this is why we needed a separate language, to have all this information to be able to super efficiently optimize things while keeping them completely safe. So that's it. Zinc is, the documentation is publicly available. The code we're going to publish under some permissive license. We've not done it yet because it's not yet finalized. But you can follow the news here, and you can also get Zinc now for if you want to try it out. We'll share it with you. Thank you. Any questions?
Okay, microphone is on the way.
Will it be possible to export generated constraint system and witness generation code for different backend to GNARC, for example?
Well, for the Bellman has ZK interface. I think somebody implemented it for Bellman. So whatever you have in Bellman, you can also export to other systems. Okay, great. No more questions. Thank you.
Okay, guys, if you have any other questions for him, you guys can talk outside in the lobby.
No, I'm just changing the batteries.